All right, let me just share my screen here from my iPad and we'll get going. These will be some notes on continuity and a little bit on limits, but not a whole lot. So this note sheet is available in the Schoology folder. I highly suggest you print it out, and I would keep them all together someplace, like maybe get a binder or something. This is the first start of our actual AP test review, and we're going to go through it in about, I think, like 5 or 6 days it'll take us to just do a broad overview, and then we'll start focusing more specifically on certain content, and we'll start going specifically toward full free response questions. All right, so first of all, we did have limits prior to continuity. I don't feel the need to do a full video review of limits, but we'll discuss those obviously when they pop up individually. So the first thing we have is what I would call the definition of continuity, and I'm going to add a little dot here. Remember, for a function to be continuous at a given x value, we'll say at x equals a, but remember a is a constant in this scenario, so like at x equals 2. First of all, the function must be defined there. So I like to say f of a exists, or f of a is defined. We must have a solid dot there, not an open dot. All right, next step, we have to make sure that our limit, as we approach that constant from the left-hand side of the function, again, we always have to have a subject to our sentence, directly matches up or is equal to the limit as x approaches a from the right of the function. And I know it's kind of maybe insulting your intelligence, but remember, f of x is y, so we're making sure that those y values match. Whenever you're thinking of a limit of a function, it's its y value. Oh my goodness, I'm looking outside and it's like slushing out like this wet snow. Yuck. Weird. And if you're wondering, I'm making these on Thursday, what is it, 9th today? So there's some very icky weather at about 1:30 in Champlin on Thursday. I just happened to look out the window here in my office. I'm like, holy crap, it's snowing. And it was 70 degrees yesterday. All right, sorry. ADD, right? Here we go. So also, we have to make sure that that limit, that place that we arrive on the y-axis from both directions, is actually at the same location as that dot in the graph. So let me meet all of those criteria at a specific a value. First of all, f of a is defined, and this is y equals f of x. F of a is defined. Maybe it's up here at 3. Okay. Next, I'm going to make sure that as I approach a from both sides, I not only end up at the same height, but it has to be at 3. So boom. So let's go talk about if this criteria is not met. Then we have what's called a discontinuity in the graph. On the AP exam, you'll get asked about discontinuities in different forms. It might be graphical, it might be analytical, or I guess it could be tabular too, but usually it'll be a graphical or an analytical question. So let's talk about a removable discontinuity. There are 2 types. But both of them have an open dot in the graph, and let's say at x equals b. This is called a removable discontinuity, because if this was, say, up here at, let's just say, for shits and giggles, up at 5, then, sorry about that, then I could remove it by saying f of b is 5, and I'd plug that hole. So, sorry, I didn't realize I had that on there. Hope I'm looking at my iPad, not at my computer screen. Anyway, so back to the graphical. So what would have happened analytically when there's a hole in the graph? Analytically, what happens is that there is this factor that cancels, and I'm just going to put like an x plus a down here. It doesn't really matter. But there's a factor that cancels. And what that does is, and it's on the top and the bottom, what that means is it's neither an asymptote because it's canceling, nor is it an x-intercept. An x-intercept occurs at whatever makes the numerator equal to 0 and does not cancel. So at x equals c, for this analytical function, we would have an x-intercept. All right, lost my train of thought here for a second. So basically what happens analytically is there's that cancellation. So, but the limit does exist. So what we do is we plug that back in. So let's go talk about that specifically with a function. Let's suppose my function is f of x is equal to, let's make it x squared minus 4 over x plus 2. And then let's say times maybe x minus 3. I don't know. So what happens on this, guys, I have the factoring on the top. And let's talk about analytically what all this means graphically. And let's go like that. So the hole in the graph, the removable discontinuity, occurs at -2. The limit exists there. There's just a hole there. What is the limit? It's what you get then when you plug in -2 for both of these. You are there. So the limit is that value. All right. Also, what happens here is there'd be an x-intercept at x equals 2 because that's what's making the numerator equal to 0. And then when the denominator doesn't cancel and there's a 0, that's where we get that infinite discontinuity. So let's go to the next type over here. So I'll erase that little analytical analysis there. All right, so let's go to the next guy here. What happens when we have what we call a jump discontinuity, which creates visually a graphical gap? We can't use the words jump in our explanations. We can't use the word gap. We have to use proper notation. Well, what's happening on this guy is that the limit as x is approaching, let's see, c, I guess, in this scenario from the left, it is not equaling, oops, and I forgot my subject of my sentence. Let's call this guy f of x, is not equaling the limit as x is approaching c from the right of f of x. That causes this non-removable. It's only removable if you can redefine or define a single point. What does she mean by redefine? I'll show you. On this guy, if I put a solid dot right here, if you didn't see what I did, go look at the yellow. If I put a solid dot right here on graph 1, now what I have is f of b exists, directions exists, but the limit is not equaling f of b. But if I say psych, f of b equals 5, then I can redefine it and remove the discontinuity. This, I cannot redefine a singular point. I have to move an entire infinite amount of points to remove the discontinuity occurring at c. Analytically, what happens when you have a graph is it ends up being presented to you as a piecewise function. So it'll say what's happening everywhere to the left of C and what's happening everywhere to the right of C. And at C, when you plug it in to the left analytics and plug it into the right analytics, you will get a different answer. So those are usually presented as piecewise functions. Next, the graphical for what we call an infinite discontinuity. It's actually called an non-removable infinite discontinuity. And again, you won't be asked those types of questions. We'll show you how this appears up on the AP in a little bit. All right, what happens when I have an infinite discontinuity at D? It means at D, I'm heading to the infinities, maybe both up or both one up and one down, but there is a vertical asymptote existing at D. What happens analytically for a vertical asymptote? It means D is causing a 0 in the denominator and it does not cancel. So maybe this is what's happening. That's just, a for instance, but there's no way to remove that like there was on this one where it canceled top to bottom. All right, so here we've got a word that I want to give you an exam tip on. When a problem says justify, it's the highest directive you could have. It's more powerful than explain. It's more powerful than show. It's more powerful than reason. Justify requires the use of. So let's go write that down here. If you are asked to justify You need to be very robust in how you answer your question. Justify implies the use of either a definition or a theorem, hypothesis, and conclusion. So justify that something's continuous means I need to use its definition, which is a three-part definition, to answer the question. All right, and it often requires just, some work and then a singular sentence, but it has to be, you can't just look at this and say, yep, continuous because -1. You might say, why is she saying -1? You'll see when I do the problem. Justify, you've got to be very, very clear and very explicit and thorough. So let's go take a look. For this to be continuous, and it says, is it? It might, sometimes I'll say justify that this is or is not, but this is an is question, which means when I'm done, I'm going to be writing yes or no because, and then I will validate my justification. All right, let's go take a look. And again, this is review. If you're going, oh my God, I don't know any of this, you might want to consider, well, whatever, you do, you boo. All right, here we go. First of all, the sign @2 being plugged in would equal this, right? So what I'm doing is I'm saying, does the sign, not just the sign, but does g of 2 exist? I actually should write g of 2 equals. And it does. Sine of -π² is the y value there, which is -1. All right, so g of x is equaling the sine of -π/2, which equals -1. Now, I might even want to continue this with an equals, because I don't have any linkage here. This is equal to the limit as x is approaching 2 from the left, because it's still that same function of g of x. Now I'm going to see if it equals the limit as I come in from the right. If the answer is no, I'll stop and write no, and I would put a little slash through that equal sign. But in order for me to decide the yes or the no of it, I need to actually go plug 2 in. I get a 4 minus 12 plus 7, -8 plus 7, which is -1. So sweet, it actually is equaling the limit as x is approaching 2 from the right of g of x. So notice in this statement, I've actually covered all three criteria. I've got g of 2 existing, right? It's -1. I've got the limit from the left equaling the limit from the right, and I've actually stated, this would be called a minimalist answer because I didn't list them all out like part 1, part 2, part 3, but I've linked it all together to cover all three criteria, and furthermore, I didn't make any linkage errors. That is all equal. Now, had I plugged this in over here and this had said +6, and so then I didn't get a -1, right? I would have had a -2. Then I'd put a slash through this equals, but I could still answer. So I'm going to say, but then, well, I would do it differently if it was not. But let's go like this. This is a yes. And maybe I should actually restate it. Maybe I should say, yes, g of x is continuous at x equals 2, right? Because, and let's talk about why. Why is it continuous at x equals 2? Because g of 2 equal the limit as x approach 2 from both directions. And that covers everything because it's got it existing, it's got the limit from the left and the right, right? And I have them both equaling -1. So that one's done. Now a graphical interpretation. This would be called analytical, and over in example 2 would be called graphical. So let's go take a look at that guy. So doing the graphical, I have over here, which one of these is false? Well, you're not going to be having multiple choice, but it doesn't matter because we're going to be thorough in our review. Is the limit as x is approaching 3 from the left equaling 3 from the right? The limit's the y value there, although it doesn't exist and there's a discontinuity. They are both 4, so that's a yes. The limit is 4. That's where I used to talk about the restaurant that you were meeting at blew up and got built somewhere else, but you came in from here and your date came in from here and you're both sitting there looking at each other at a place that does not exist. all right? So that's a yes. The limit as x approaches 6 from both directions, that's what that means, is 0, right? And f of 6 is also 0, so that's a yes, and that's why we have continuity there at 6, by the way, because it's meeting all the criteria for a continuous function. Is the limit as x approaches 5 from both directions equal to -2? Let's approach 5 from the right. I'm down at -2. And now let's approach 5 from the left, and I'm up at 3, so that's the false one. All right, so which of the following is false would be that one. So that's it for the notes. Now what I'm going to do is actually the most important thing. I'm going to say, well, how does this present itself? I went to the 2018. If you want to know where this one is, it's a pretty recent one. I was actually a reader for this problem, so I know this one very well. By the way, at the AP reading the way it used to be done, it's going to be done differently this year. I don't have any details on that yet. I just got a text message from ETS, the Educational Testing Service, and I think they are figuring things out, and it just said that more information is to come. All I know is the reading will be done in the comfort of my own home, if I choose to do so. And that's all I know. But what used to happen is we'd all meet in this convention center, and we'd get briefed on a problem for an average of about 2 hours. And by briefing, it means if I was assigned to this problem number 5, they would take us into this big auditorium for all the people grading number 5 on AB. And the question writer and the question leaders would give a conference. They'd usually talk straight for 1 hour. You weren't allowed to ask questions. We're not allowed to take pictures. Nothing. You just listen and you write like crazy. And they tell you how to score each of these, and then they give you a bunch of student samples and have you practice. So it's very intense. So I was assigned actually to this problem, and that's why it brought it to mind for this particular topic because of Part D. And the interesting thing with Part D is almost no kids got a 9 on this one. And it was because of Part D. There was a little detail that they did actually count in the scoring, and I'll show it to you later, that most kids did not state. And then even those who did invariably made a mistake somewhere else. So we gave almost no 9s globally on this problem, and hence in 2018, there were no perfect AP Calculus AB scores, and I'll show you that document as well. But let's go take a look at this guy. And I'm mainly going to focus on Part D, but I want to talk about A, B, and C. All right, sound good? So in Part A, if you're asked to find the average rate of change, the AROC, you would have been finding, hopefully you know this, the slope of the secant line, the average over the 2. Slope of the secant line, f of b minus f of a over b minus a. So you would have done f of pi minus f of 0 over pi minus 0, and using this function f. Hopefully we would all get those points. For Part B, the slope of the tangent line is the instantaneous rate of change, or the IROC. That's the derivative. So hopefully you would have known that you need to go up and do the derivative. Hopefully you would have recognized product rule and remember your rules. It's first d second plus second d first, and then we just go plug in our 3 pi halves. We actually don't even need to know the unit circle because they allow you for, now wait, be careful what I just said. You need to know your unit circle, 100% hands down. But for an FRQ, you are allowed to leave 3 pi halves. It drives me nuts. Hated correcting it when kids did that, when they just left cosine 3 pi halves, instead of realizing that, hey, at 3 pi over 2, cosine 0, and it cleaned the whole thing up so nicely. There are a lot of kids who actually made sign errors on that, though. So note to self, maybe just leave it in there. You can't leave a function as your answer, though. You actually have to go plug in the numeric. For Part C, we're going to focus on that a lot in a few days, but absolute extrema, so this is just a brief review to get to Part D. Absolute extrema, whether they're maxes or mins, occur at endpoints. So you had to evaluate f of 0, plug it in, f of 2 pi, plug it in, put it on a candidate table. And then also on your candidate table is anywhere where we have relative maxes or relative mins. Where do those occur? Let's make one where the endpoint actually, let's, if I go like this, see the endpoints can be absolute extrema. On this problem, the left endpoint, like in this graph, the left endpoint is the absolute maximum. The absolute minimum occurs at a relative min. So on your candidate table, a 0 and f of 0, a 2 pi and f of 2 pi, and any of these relative extrema. Remember, that occurs when we set our derivative equal to 0, and we get our critical values and put those on the table as well. But the point of this problem was to get to part D. All right, and we're going to run through all of part D because this one popped into my head 2 times this week. I'm like, oh, I remember reading a problem that had, and number 1, continuity, and we'll talk about the other skill in here that we've done recently that this problem referenced. So if you listen to nothing today, this is the most important one for you to absorb. Again, if you're just doing these to complete tasks, you're going to get your little homework points, but it's not going to do you any good in the long run. So really try to understand this letter D because it's a good question, and very few kids got all this. Had 3 points attached to it. I'll tell you what those are when we're done. So let G be a differentiable function. That's going to be really important coming up, such that its y value at pi halves is 0. Then they give you the graph of G prime. Now see, this is really, this guy too is now popping into my mind for a third reason. Number 1, because it's going to reference a continuity thing, obviously, because that's what I'm reviewing today. Number 2, you're going to see as we go through the problem. The third thing is that this problem could very well appear on this year's test because I don't know what G is. I can't go into any sort of software or any computer problem or anything and enter this and get any kind of answer off the internet because it's giving me a graphical of G prime and I don't know what G or F are. So this is all about the concepts behind it. So this guy just hit my radar for a third reason. All right, let's go take a look at it. It says to find the value of the limit. So this is a limit question, or state that it doesn't exist. Remember, the first thing we do when evaluating a limit is we plug pi over 2 into the top and into the bottom. Let's go plug it into the top. So let's go the limit as x approaches pi over 2 of f of x. Okay, let's go see what that is. All right, let's go to the top and let's go plug in a pi over 2 to f of x. I would get e to the pi halves. Let's go ahead and write that. Times cosine pi halves. Now, if you don't know your unit circle, this is going to trip you up. Cosine pi over 2 is the x value there, and it's 0. So the limit as I'm approaching f of x, pi halves of f of x is 0. So the top is a 0. Now I'm going to do the bottom. This is where kids lost the point. You might say, well, it's g of pi over 2, which equals, they told you, 0. However, if that's what you wrote, you lose a point because you don't know that these are equal unless the function's continuous. How do I know the function's continuous? Because they told me it's differentiable. You could have heard everybody in that conference room when they said there was a point for that going, oh crap, my kids are not, including me, going to remember to state that. And they didn't across the world. I think I came across, honestly, in the thousands and thousands that I graded, because I graded this for like 3 days for 8 hours a day. You don't grade all the questions. You usually just grade 2. Sometimes you get put on a 3rd. But this was the majority of my week was spent on this problem, and I think I came across 1 or 2 people who actually did, in part D, say, since G is differentiable and therefore continuous. They did not state that, and that was one of the points on the scoring rubric, and we were all like, what? But the thing is at least it was fair because we were all grading it the same way, so it didn't affect kids' overall ranking. It just kind of went into the stats pool. All right, so what do I do when my numerator goes to 0, and my denominator goes to 0. We do not write equals 0 over 0, but we do know that we launch into L'Hopital's rule, and that was from earlier last week. So I'm going to write therefore, using L'Hopital's rule. They did not actually have to state that on this problem, though, but I always advise it. We have the limit as x is approaching pi halves of f prime of x over g prime of x. All right, well, g prime of x at pi halves is off the table. It's going to be something over 2. And then I need to go evaluate f prime at pi halves, which I would have found f prime's model in part B, and I just plug in a pi over 2. So I'm not going to go do that, but it was just some number over, I think it's e to the pi halves if I remember right. Let's see how well I remember grading this one for 3 days. I'm going to put that on there, and then we're just going to put a question mark. I'm going to go show you the scoring rubric, and then we're done for today. You will have 10 multiple choice on limits, continuity, and 1 FRQ to do. You're going to score them, and then you're going to enter in a reflection form. All right, so that's it. Normally the notes will only be about 10 minutes, but I did add this FRQ to it, so but don't think they're going to be this long every day. So what I'm going to do here is I want to share my desktop with you. And the reason I want to share my desktop with you is because I want to show you the scoring on that problem. So let's see how well I remember. Oh, it was negative pi e to the pi s, but it's been 2 years, so at least I kind of remembered grading this one like crazy. But notice this guy, g is continuous. If you did not state that, you didn't get the first point, then applying L'Hopital's rule and then getting the correct answer. So you would have had, a lot of kids got 2 out of 3. They knew to go to L'Hopital, and they had this correct answer down here. Not knowing your unit circle would result in a sign error. All right, this was that candidate table I told you had to make. Up here, slope of the tangent line, just a derivative, and up here was our AROC, or the slope of the secant line, but we didn't do that whole problem. Then I'm going to show you in 2018, just so you don't think I'm making these stats up, 2018. They have all the AP tests in here, and they always say, you know, how many people aced it. So 1 student in Chinese language across the world aced it, 16 in Spanish aced it. Again, this is global, so this is worldwide. Not many people ace it. 18 for drawing. Let's go to one you might be interested in, though. Well, I'm not saying you shouldn't be interested in. One that a lot of you take. Computer science, 214, that's a lot, acing that one. Bad news in English literature in 2018, stats, 1 student aced it. But you'll notice biology, looks like nobody aced the bio one. If they don't say anything, then it means nobody got a perfect paper. So history, 6 students worldwide, but let's go down to, if you're interested in this data, by the way, you should be able to see my URL up on top. So Calc AB, see how they don't say. So nobody aced it, and it was really, I know it was because of that last question. You'll notice that was 5, question number 5, and this is really interesting because it was surprising how poorly kids did do on it. 26%, like a little over a fourth of all kids who took it couldn't answer anything on that one. And that problem was actually very easy to get at least a 5 out of 9 on. We should know our average rate of change. We should know to find critical values and put them on a candidate table for absolute extrema. We should know that the slope of a tangent line is its derivative, and it was just e to the x and cosine, and we know their derivatives. So it should have been, we should know L'Hopital's rule even though we just learned it. I think that was an easy 5 out of 9 for you guys. Anyway, that is it. I'm going to end this meeting. And you guys have a great one. Don't forget to do the rest of this, though. I always forget. I've got so many windows open. I always forget